concept. Thanks for joining us. My name is Ahmed Ismail. I'll be your host along with the main speaker, Mahmoud Serour. Mahmoud currently works as a team lead for the ADAS R&D team. For those who are first time to join us, Embedded Meetup is a non-profit professional community with focus on sharing knowledge and providing opportunities to fellow professionals to sharpen their skills and get exposed to the latest technologies. We have been working for almost 2 years. Our main activity is hosting webinars that address the latest technologies, in addition to other activities such as evaluation program that coach job seekers to get their first job through simulations and the training on the hiring process. Shortlist candidates get recommendations from the community, so we are connected skills job seekers with companies having vacancies. Although the largest percentage of our audience are from Egypt, but we have colleagues from North Africa and Far East. We are greatly honored to have a showcase for Bright Skies milestone, which is a milestone for the whole embedded systems market in Egypt. Bright Skies was founded in 2012 as an engineering service, then decided to invest in R&D by developing the self-driving system that currently in the POC stage. Mahmoud Serour will be our guest to tell us the full story and the challenges they met to reach the point. Okay, then let's start the webinar. Please notice that questions will be handled after the presentations for 15 minutes through YouTube chat. Thanks, Mahmoud, for volunteering for today's webinar, and the floor is yours.
Okay, so thanks Ahmed for having me tonight. I'm really glad to having this webinar to talk about our self-driving proof of concept. So let's start. So just a few words about me. I am 2016 graduate from Alexandria University, Faculty of Engineering, Electrical Control and Power Department. In college, I was a co-founder of a robotics team, which is well known across Egypt, I think, called Made in Alex. Mainly, we joined a lot of robotics competition, starting from underwater robotics like ROV, going to Minesweepers, International Robotics Challenge, which is about lane keep and lane following robot, and also as well the famous competition which called Rubcon. The team in the past 10 years conquered a lot of regional and international competitions, and I'm really proud to be a co-founder of that team. In additionally to my experience in the college, I have 3+ years of experience in system engineering with the main focus on ADAS applications, most of them in Brightskies. So mainly I developed several fair operational systems for brakes and ADAS system for a level 4 vehicle. Also, I was a part of the development of system architecture of the Yeezus ADAS as well as development a torque management system for our second version of R&D, which is about electrification. Recently, starting from this year, 2019, I was leading the ADAS R&D activities at Brightskies, which I will talk about later. So what we will talk about in this webinar, a short introduction about our company, vision, BrightDrive, which is the product name of our self-driving proof of concept, what's about, what the challenges we have faced, and some insights that you will see for the first time, and what we are going to provide for others, like possible services. Then we will end with a question and answer at the last of the webinar. So let's start about the company intro. So as Ahmed was saying, Brightskies was founded in 2012 with the headquarters in Alexandria with just 2 engineers with main focus on high performance computing. So throughout these 8 years, we now have offices in Cairo, Dubai, and Germany as well. We started to begin in the development or joining the embedded systems activities in 2016 with main focus on functional safety, system engineering, software development, and process development as well. So in general, we provide services in safety critical applications in automotive, in high parallel computing and virtualization, and in enterprise software solutions. Throughout those 8 years, our software engineering team, or let's say our engineering team, are about 120 plus, allocated mainly in Cairo and Alexandria, and at many customer sites as well. We have customers in Europe, in Saudi Arabia, in Dubai, in Gulf in general, in Europe, in USA. Um, we have dealt and provide many solutions and services for multiple of OEMs and automotive, well-known automotive members. Our management team is as follows. So Khaled Lamraoui is the CEO with 25 plus years of experience, previously Intel Director of Middle East, Egypt, and North Africa. Hisham Arafa is the Chief Operational Officer with 24 plus experience, previously was Valeo Egypt R&D Director. And then we have Hussam Yahya, which is the Chief Technical Officer with 14 years experience, and he was previously functional safety expert at Valeo, and also as well a functional safety expert at Brightskies. Then we have Rania Sabra, which is the Vice President of Enterprise Solutions with 20 plus years of experience, and previously a software operations manager at Advansize. Then we have our engineering director, Karim Morsi, with 14 plus years of experience, and previously was leading the service area in IBM, generally in embedded IoT and mobile applications. So I think most of you will be curious about R&D activities in general, because as an automotive service provider, we provide like the traditional services regarding functional safety, system engineering, and software development. So mainly, I will talk about the R&D variant of Brightskies regarding the ADAS, which is a product name is called the BrightDrive. And actually, the BrightDrive is not only the R&D variant we have at Brightskies. So for ADAS, there is BrightDrive, and for powertrain and chassis, we have BrightBus, which is mainly about electrification. So we are working on the development of battery management system, powertrain system, electric steering system, and brake system as well. So in general, we will electrify all the components in the traditional or conventional vehicle that works with internal combustion engine. This is an R&D variant, and currently we are working on the battery management system. We have as well Bright Infotainment. We are developing our own infotainment, either for electric vehicle or for conventional vehicles. So infotainment is a big word, may involve central display, cluster display, co-driver display as well. But for the first variant, we are developing our own cluster display as a first start. And then we have a Bright Charge, which is about a smart application for charging points to know which charging stations are available and which are not, and you can book charging stations and so on. So mainly those are the 4 activities for R&D for Brightskies in general. And tonight I will talk mainly about BrightDrive. So I will try to give you as much as information as possible as I can without exposing our work. So you can excuse me if I couldn't answer all the questions in the Q&A section. I will answer as much as I can, as long as I don't expose the work we have done. So mainly our vision. So starting from this slide, we will mainly targeting the BrightDrive, or the R&D self-driving variant from Brightskies. So mainly we have a short-term vision and long-term vision. The short-term vision, which is about the proof of concept that you have already seen in the video, which I will already as well show you in the last of these slides. So the short-term target of Brightskies regarding the BrightDrive is ramping up the team knowledge. So we created a team mainly based on AI or deep learning engineers, algorithms engineers, software development, system engineers as well. So the main target was to ramp up the team knowledge in self-driving cars in general, gives them like some hands-on experience on a real project, then getting the platform ready for deploying the AI algorithms. And what I mean by platform is not just the sensor setup, but getting the platform ready on a real vehicle. Because, for example, we have a lot of research centers and R&D labs, R&D facilities that are working on AI algorithms. And when it comes to testing on a real environment, on a real world, they use like a golf car, for example. But our main focus was to deploy those algorithms, even if they are sample, on a real vehicle. Because later on, this real vehicle will be, there will be much heavy computational algorithms will be deployed on this real vehicle, which we can simulate as much as possible, as real as possible to the real environment. And then the purpose of this short term is to ramp a demo, which is level 3 or 4, ADAS on a real highway environment, which is mainly mixture between straightforward approaches and complex ones, which can be patented later. So the demo, we can say that the demo in general, you have seen in general, is a mixture between straightforward approaches and complex ones. So either we develop it from scratch or we added some enhancement to an already well-known approaches. The customer for this short term is internal, so internally for Brightskies. And for the first demo, we can say that the short term is finished. Then we have a long-term vision, which we will have a fleet of cars to collect data sets from roads. So if we will work in Egypt, then we'll collect data sets from Egypt, can be from Gulf, can be from Europe, which mainly is customer dependent. Then we will patent complex approaches either in our short term or in our bigger vision in long term. And then we will have like concrete ADAS layers with competitive evaluation metrics for each layer. So I would like to explain a bit here. So for ADAS layers, we have perception, localization, mass planning, and motion control. For example, when you try to evaluate something like perception, we use a term which is famous for deep learning or AI in general, the mean average precision. So we are saying that the evaluation metric for our perception layer is to have like X mean average precision with X range. It can be 100 meters, 400 meters, and so on. Then the localization matrix is in accuracy in centimeters, how accurate you can localize yourself. And then the path planning, when it comes to evaluation metrics for path planning, it is really tricky here because there is no quantitative thing that you can measure on how successful is your path planning. But we measure it in how it is capable of handling corner cases or unusual situations or a situation that it has never seen before. If you are talking about an AI, not a straightforward approach or a classical approach. And then we have motion control. Motion control mainly how we are able to track our trajectory. Then for a part of our long term as well is to be ISO 26262 compliant. So up to this date, we don't have a functional safety, don't have functional safety process. Also, we are a functional safety experts, but because we had like very tight schedule, so we couldn't make it ISO compliant. And one major thing as well, because we already deployed our setup on a vehicle, so we cannot change anything in the hardware. And when it comes to functional safety, we need to go through the whole cycle, starting from the system, the big thing, going through the software and the hardware. And I think a question that we will have in this webinar and it is international. The international community talks about is how that you can guarantee the safety of such thing, because when we go for the ISO, if some of the joiners or the webinars knows ISO and the functional safety process in general, there's nothing exists in the current standard that says how to describe the safety or how to assess the safety of your solution if it is like level 3 or level 4. That's why there was a variant called SOTF, Safety of the Intended Functionality, which is mainly targeting those critical applications, starting from level 3 and so on. Yet it doesn't provide the complete process of what you actually should do to prove that your system is safe. However, it involves some fault injection test cases, which can help you to like provide a safety case later for such assessment. We are targeting as well to be a process compliant, mainly for the guys who was working for the automotive will know SPICE, so we are targeting SPICE. I think level 2 will be a good start for us, but we are targeting like a basic process for the long term. Also that we have already a process in short term, but I mean like a certification. Then we will formalize the ADAS layers I just talked about, perception, localization, motion, and bus planning in levels. So I will talk about the levels of autonomy, just a quick overview on levels of autonomy, because I know already that there was already several webinars talking about autonomy and self-driving cars. And then our bigger vision is to have like the first Egyptian electric autonomous shuttle or bus, because as I told you, we already have a variant in R&D that is mainly concerned about electrification. So we would like to combine all of our R&D activities together, either is BrightDrive, BrightBus, and Bright Infotainment, or Bright Charge in one complete vehicle, which is made by our company. So I will just give a quick hint about the ADAS levels. So mainly when people ask me about the ADAS level, or I would like to illustrate about the ADAS levels, I do like the following. I start with level 0 and 5, then going down from 5 and so on. So level 0 is no autonomy at all. Level 5 is full driving automation. In all places, the driver doesn't have to interpret or intervene in ADAS operation. No constraints in weather, no constraints on lighting condition, no constraints on the place. So whatever you are, the vehicle should pick you up from your location and move to your destination. And if there is any fault or failure in the system, it should be the responsibility of the system to pick you up to a safe state. That's why in level 5, there is no need for a steering wheel, because there is no need for the driver to exist. Examples, which is in research, a company called Zoox, they are developing a car which should be level 5 autonomy. And why I say so, because they have no steering wheel actually. Zoox got acquired from Amazon, I think, from 3 months. And a good example that could be an example for level 5 solution, yet it is not, there is no rumors or there is no self-driving system exist in that car, is the Mercedes Avatar, because there is no steering wheel as well. And mainly you see that the wheels are not conventional wheels, they are Omni wheels. So Omni wheels are special type of wheels that you can move in right or left direction without steering. So with some equation, with some mathematical equations, the wheels are oriented at 45 degrees, and then you don't have to steer actually. So you move slideways to go right or left. And then we have level 4. So level 4 is like level 5, but the operational driving domain is constrained. And when we talk about constraints could be like about the road marks, lighting conditions, weather conditions, a specific area of the road, which you can later decide by geofencing, for example. And as well, the vehicle control, monitoring, fallback is all the responsibility of the self-driving system. And the driver doesn't have to intervene as long as you are within this operational driving domain. And if the system detected that the system is going out of that operational driving domain, he should give back the control to the driver or reject engaging the self-driving system from the start. Examples for this are Waymo, and I can say us as a first stage. We are still working on that, but what we have today, I can say we have a level 4 proof of concept. Yet we didn't show all of our features because of some limitations. Most of them are non-technical, which I will talk about later. But in general, the development of our system, I can say that it's up to level 4. Then we have level 3. So level 3 is like level 4. However, if there is any failure in the system should detect this and give the driver the control in a specific period to intervene. So in general, if there is any failure in the system regarding hardware or software software error, the system shall give the control back to the driver in a specific timing. This specific timing shall be safe for the driver to intervene and like mitigate the collision for other vehicles, for example. And still as well, it is a limited operational driving domain. So responsibilities of ADAS in general, vehicle control and monitoring, and fallback, we can say it is a shared responsibility between the driver and the ADAS. So the ADAS monitors and the driver takes control. And examples for this is Audi A8. So I think most of you have seen the commercial video of Audi, which were talking about different kind of sensors, LiDAR cameras, ultrasonics, and so on. It's a really nice video. And we have Remax Concept 2, which should be already in the market in the next year. And then we have the partial driving automation. And by the way, there is Honda as well, published some news that they are already making a level 3 in their next release. Then we have partial automation. So partial automation is like the conditional driving automation, except for one thing. So for level 3, we say that the driver doesn't have to monitor the self-driving system. He just have to stay focused and wait for the driving system warning, for example, to ask him to take the control. However, for level 2, whatever the ADAS is doing, the driver shall always monitor the ADAS or the self-driving system. So in all cases, the driver should monitor the ADAS decisions. The monitoring itself, we call it object and event detection and response. For the fallback, we call it the dynamic driving task fallback. Some examples are Super Cruise for GM, Nissan ProPilot, and Tesla. So even so, Tesla have a full driving beta version for all their users. They cannot say that for the driver you shouldn't like leave your steering wheel. So there is when you engage the Tesla autopilot, there's a disclaimer that says that you always should stay focused, and this is a beta version and still under development. So you should still focus. That's why the object by definition for the SCE, so these definitions are according to SCE standard, by definition is still level 2. Even so, there is a variant that can achieve a full self-driving autonomy. And this is because that either the fallback or the object and the event detection and response are the responsibility of the driver. And then we have the driver assistant, which is mainly controlling one of the vehicle motion axis. So either controlling the lateral control, like lane keep assist, or controlling the longitudinal motion, like the adaptive cruise control or the cruise control. So mainly those are the level of autonomy, and what we are trying to achieve, or what we are claiming right now, that we are level 4, between level 3 and 4. Okay, so The team structure in general, we have for BrightDrive, we have a project manager, then we have a technical lead, then we have 4 different teams. The first team is sensing and perception team, which is mainly concern is to develop an environmental model for everything related to the road. So road segmentation, road boundaries, objects detection, like pedestrians, vehicles, object prediction, lane detection, infrastructure detection. I will explain later in a system architecture slide. But in general, anything related to environment is the perception team responsibility. That's why you find that we mainly have a lot of people working on AI, deep learning, and some algorithms engineer, which is our classical algorithms, not deep learning. And then we have the driving logic team, mainly the team responsible for localizing the vehicle, which should tell you where the vehicle are with respect to global coordinates and bus planning. The trajectory planning itself to go from the source to the destination, or from the input from the user to the destination. That's why we have, for the driving logic, for this phase, we had like an approach to go better with the classical approach as a start, as it is more straightforward than going with the AI. That's why we have like more algorithms engineer than the AI engineer for this part. And then we have the motion control team, which is one system engineer, mainly developing the lateral and longitudinal controller to control the vehicle. And then we have an application team, which designed the application which should call the car. So in general, initially the team started with 12 plus engineers and ramped it down throughout the project to 4 to 5 engineers because of because of business issues, and at the start you have a lot of problems, but when it comes to testing or deployment and testing or verifying your output in a real environment, you don't need that much engineers, taking into consideration that there is only one car. Okay, so what we are trying to achieve here, mainly what we are trying to achieve, or what we have shown in the video, that you should that you have an application which is mobile or desktop application. You call your car to pick you up from your location, and then you put a specific destination, and then the car will come to pick you up. Can go through gates, so the video include a gate. Will go through a gate, then pick you up, then go to any destination you desire within a described operational driving domain, which we can check later using geofencing. So mainly in general, in general, the vehicle, you can call your vehicle using an application, which we call summon by application. The vehicle comes to pick you up and then moves you to the desired destination. We'll keep the lane if there is a lane. If there is any failure in the system, the vehicle will go to a safe state or a safe trajectory. So in general, we have 2 components. One calculates the normal path or the trajectory path, and one calculates the safe path. So in general, if there is no issue, the vehicle will go on the main path. If there is an issue with the sensors or the software itself, the vehicle will move to the safe trajectory, which should be like, if we are on a highway, it should be the service lane, for example. So the vehicle cannot stop at the middle of the way. And when we are talking about failures, what I'm mentioning here, and when I'm saying level 4 as well, I'm mentioning from a software perspective, because right now we don't have any access to the vehicle hardware. So when I say level 4 or safe states in general, I am meaning the software stack which you already wrote by ourselves. And throughout this destination, the vehicle should do the all ordinary dynamic driving tasks. So it should steer, it should track speed, it should follow lead vehicles. If there is some traffic, it should bypass or maneuver around these vehicles while keeping safety. It should avoid other cars during lane changes. So the usual dynamic driving task for all drivers. And what I would like to mention here, we are not highway assistant, because we are not like a combination between adaptive cruise control and lane keep assist. Actually, there's further complex algorithms, because as long as you have waypoints from the source to the destination, you have a pickup location, you have destinations, then we are not a highway assistant, because we are already for example, we already detect the traffic lights, we detect the road marks, so we have an awareness of the environment in general. So let's talk about, when we say level 4, let's talk about the operational driving domain in general. What constrains us for the current phase? So what constrains us for the current phase is a highway environment, with highway-like environment with visible lanes and landmarks, good weather conditions, good lighting conditions, normal friction coefficient, and no construction sites. So let's discuss one by one. For the current phase, the highway was actually the most easy thing to do, because in general, in city roads, we don't have lanes and we don't have lane marks, and even don't have rules to constrain the driver in Egypt. And since we are on Egypt, so we needed an easy environment that we can test. So in general, the simplest thing to go or to start with is the highway. Even if we in Europe, the simplest thing to go with is the highway, from my perspective. And then we have a good weather conditions, no heavy rains, because we already purchased sensors, some type of sensors. They have the highest IB, but for example, in Alexandria, it really rains so heavily, so there is no kind of sensors that can resist that kind of weather conditions. And then we have good lighting conditions. Tunnels are accepted as long as they are with good lighting, so the cameras can see well. And the nominal friction coefficient, so asphalt, because for example, I will show you some insight. The initial track or test track for us was sand, so it was really difficult to test, because when it comes to change between sand to asphalt road, there's a lot of heavy tuning and a lot of work is done here to adapt the vehicle to such environment. And no construction sites. So this is just a safety precaution for the driver itself. However, as I told you earlier, we already have an awareness of the environment itself. And then we have some driving constraints. Speed is limited to 80 km per hour and is tested in 80 km per hour. So the demo video were not shooted at 80 km per hour because we were in closed environment. The driving in forward direction, so no reverse direction. We keep distance between the lead vehicle and the ego vehicle, which is our vehicle, is up to 50 meters according to the international standards. So in the international standards by law, either keep 50 meters or a specific amount of timing, which is variant through different countries. EBB is an abbreviation for electric parking brakes. So we only allow the electric parking brakes. So in general, we have two types of brakes in the vehicle: the conventional brakes, which has the usual conventional features like the ABS, EBD, and so on, and we have the electric parking brakes. It is electric, not manual or conventional parking brakes. So we are only allowing the parking brakes to activate during a safe stop. So in general, because if you allow the parking brakes to activate, it doesn't use the hydraulic actuators, it uses some electric motors attached to the rear wheels. So in general, it could, if you allow the EBB to activate above a certain speed or in a high speed, it can put you in a hazard. And instead of rescuing the driver, you put his life in danger. That's why we are only allowing it to activate during a safe stop or during the level 4 fallback. And before activating it, we are alerting the driver. And the only case we don't do so is when the time to collision is less than 2 seconds. And this value was really tested and done by some calculations with respect to how the time given to the driver to interact or intervene, and the distance we can see or detect the vehicle in front of us, for example. Minimum tire inflation and fuel are monitored by the driver because we don't have such info provided by the vehicle. The loading limitation is within the vehicle limits, so we cannot overload the vehicle because, as I have said before, and I will say as well, we don't have a specific vehicle model for the vehicle because we didn't design it. We just bought it and we done some testing to know the vehicle parameters, which constrain the vehicle model. We talked about the longitudinal distance. This is the lateral distance. So between the vehicle and neighboring vehicles is limited to be within the lane boundaries, so less than 1 meter from sides. This value as well was estimated with respect to the detection range from the side cameras. Let's talk about when it comes to our sensor selection. So I didn't mention a specific degree for field of view or specific range because, as I said earlier, I'm trying to share as much as information for the current term or for the current solution. So mainly we are using a solution that is based on cameras, radars, and GPS. And we don't use a LiDAR, which should be a question, I think, in the question and A section, because a lot of people asked me and were complaining, why don't we use a LiDAR? So let's talk about the sensors in general, and I will answer this question in this slide. So we use 6 cameras, 2 megapixel, 2 narrow field of view for stereo configuration. So we have a stereo configuration as you have seen in the demo, and we have 4 wide angles for the side cameras, and 1 top wide angle and 1 rear wide angle, and all of them are 13 frames per second. And we have 5 radars. They can work either on long or short range simultaneously. And actually, the field of view is a function of the range. So this should be FOV, not FPV. Field of view is a function of the range. And then we have in corners in conventional ADAS system, the short range radars are in the corners for blind spot detection, or when you try to lane change. And for the long range radar, it is mainly in the front to fuse its data with the camera, with the wide camera, for example, and the stereo cameras as well. And then we have a GPS plus an IMU integrated system for which help us in the vehicle localization. And when it comes to vehicle selection, because there was a question as well, which constrains you when it comes to vehicle. So in general, there is no constraints in a vehicle, as well as you are pretty sure that it has electronic steering, electric brakes, and electronic throttle control. And back to the question regarding the LiDAR, when we started this project, we adapted the idea of having a complete level 4 system without having a LiDAR. This could be wrong, this could be true. We will never know unless we publish our patent. But for example, there's a lot of consideration when it comes to sensor selection. One is the budget, and when we search about the highest budget sensor, it should be the LiDAR. So when it comes to production vehicle, you should try to avoid as much as possible having a LiDAR, despite its no one can deny its efficiency in depth calculation or accuracy in depth calculation and so on. But when it comes to budget constraints or deploying in production vehicle, the most costly thing is the LiDAR itself. So we adapted this idea of having or developing a system without a complete LiDAR, and taking into consideration that we can achieve things similar to the LiDAR using cameras and radar fusion. Mainly when it comes to depth estimation, we use a camera-like approach. It is not accurate as LiDAR, but it is sufficient for level 4 driving. I claim to be sufficient. Taking into consideration that this is for a QM level 4 ADAS system. However, when it comes to ISO or safe level 4 system, in general, the ISO likes the diversity between sensors. So when we talk about fail operational, we talk on the hardware, on the software side as well. So if there's a failure on one of the cameras, you should have a diverse sensor. So in some tasks, you will find that the only solution you have is camera. And if there is an error in this camera, you should have a LiDAR, for example, because this is a diverse sensor. And I think most of you have seen the Tesla full driving beta. They are not using a LiDAR, and by the way, they are just using one front radar at the front, and they achieved full autonomy. So I would rather the question to be is not why you don't use LiDAR. The question should be, how did you manage to do the LiDAR job with cameras or with cameras and radars? This is the right question that should be asked. And this is a setup on the vehicle. So as I have said, that we have a corner radar by each corner. We have a front radar. We have a GPS system. We have an ADAS ECU. We have a camera per each side. We have a rear camera. We have a wide camera, and we have a stereo setup here. And then we have, in general, we have 3 ECUs, one for the ADAS or for the self-driving system. And we have 2 ECUs, one which is vehicle dependent. We call it vehicle control unit or vehicle control ECU. It changes with all types of vehicles. So if you have an Audi, then you have a specific vehicle ECU. If you have an Passat, you have a specific vehicle ECU. If you have Skoda, you have another vehicle ECU. If you have a Mercedes, if you have BM. So it is vehicle dependent. And then we have what we call a gateway ECU. This is mainly to transform the communication protocol of one sensor to another. So for example, let's take an example, the radars communicate through CAN. It requires one CAN channel for each radar. However, for the ADAS ECU interface, for example, it could use Ethernet but doesn't have any CAN interfaces. So in that case, we use that ECU to make a gateway to transfer the communication protocol from CAN to Ethernet. Could be CAN to serial, but in general, what we implemented CAN to Ethernet for those specific cases. We tuned our field of view design on MATLAB. So we placed our sensors with the vehicle dimensions and so on. And if you can see here, we have a gap of blind spots. This blind spot was actually tuned in-house. So we already set up the sensors on the vehicle, and we opened all the cameras and opened all the radars interfaces, and someone was like moving around the vehicle to see if there's any blind spots or not. So in general, what we have today, we don't have any blind spots. We don't have any blind spots. And when it comes to front or rear sensing, we have a redundancy between cameras and radars. When it comes to sides, we don't have a redundancy. We have a region that doesn't have a redundancy, which we are already depending on cameras. What I would like to talk about as well is the safety concept of the vehicle. So in general, it is not an ISO compliant, and it is not an ISO process. So I'm using the same annotation. So in ISO, we have something which is called functional safety concept and technical safety concept. However, for the time being, we have a safety concept. We have some constraints or some switches that control the vehicle to a complete stop or control the vehicle behavior or the ADAS behavior in general, just to make it as safe as possible to claim that we are level 4. Today, we are not manipulating the vehicle or bypassing any safety constraints. So, for example, we have a vehicle which could contain ADAS features like cruise control, adaptive cruise control, emergency braking, lane keep assist. we are manipulating these features to achieve the motion control task or the dynamic driving task. However, we are not bypassing false inputs for these features. So, for example, we are not saying that the vehicle speed is 10 kilometers per hour while we are moving at 80 kilometers per hour. And this actually helps us a lot because it gives us a safety layer. So in general, we have two safety layers, one which is by the vehicle design. For example, you cannot give reckless steering while the cruise control or adaptive cruise control is on. So for example, you cannot steer by 100 degrees and you are engaging the ECC at 80 kilometers per hour. The ECU itself or the cruise control ECU or the vehicle in general will reject your comments and will not accept your reckless steering inputs. And the second layer is by our design. We are limiting the commands given to the steering wheel and giving to the acceleration or deceleration profiles for the vehicle. And then we have two separate power switches. So the power switches were not visible in the demo, but they are in the compartment unit. We have two power switches. One switches from the ADAS ECU and one switches from the vehicle control ECU independently. So if you switch it off the vehicle control ECU, there is no commands sent to the vehicle at all. If you switch it off the ADAS ECU, there is no commands as well given from the ADAS ECU to the vehicle control ECU independently. So in that case, you can switch off your system from two places, not from one place, and they are completely dependent from each other, and they are actually just power separation. At any case, if you don't feel comfortable as me in the video in sitting in the passenger seat on not the driver seat, so I was a bit comfortable. But if you don't feel comfortable, if you are sitting on the driver's seat, if you give any torque to the steering wheel, it will beat the ADAS steering torque at any time. So the torque given by the driver can beat the torque given by the steering wheel or the self-driving system in general. If the driver hits the brakes, the system will be disabled automatically. We have an automatic emergency braking mechanism. We are not relying on any mechanisms by the vehicle or the emergency braking feature in the vehicle. We are implementing our own emergency braking, and we have actually two redundant driving logic. And a common question here, why you have a two redundant driving logic, but we don't have a two redundant perception. Actually, because this is a platform limitation, we couldn't deploy like several algorithms on the same camera source or the same sensor source. It is achievable and doable, but will take a lot of computational resources and a lot of development. Something much easier to do is to have two redundant driving logic. So you do have two localization layers, you do have two bus planning, and then there is some sort of comparator that compares between both calculations. And then one calculation is which is like logic for the vehicle model or for the current situation being. The comparator choose the best option from these two redundant driving logic, which is, by the way, one of the famous concept in function safety, is to have two diverse logics, and then you have a comparator which compares between these inputs. And then we have a global safety monitor, which I would like to call Brightskies Angel. So Brightskies Angel or BSA usually monitors all the inputs from the driver, from the vehicle, the environmental model, the localization data, the hazards, and so on, and decides if there is an upcoming hazard or not, with some levels for this hazard. And will the vehicle will be able to maneuver around this hazard, or will be able to mitigate this hazard, or it should give the control back to the driver? Should it produce some beeping sound, or should it hand the control? Should do a maneuver? Should it do a safe stop? So in general, this is one of the complex things that it doesn't have like a specific architecture in general. We talked about safety concept, and now we will talk about every team responsibility or every team functions in general. So S&B, as I have said, stands for sensing and perception, and this team main responsibility is the following: 2D object detection and 3D object detection tracking. So on a 2D level perspective, we are detecting the objects using cameras and using radars. And then when it comes to tracking, we would like to track the object, including the depths. That's why I say it is a 3D tracking and 2D object detection. And then we have a complex system which is called the scene understanding, which mainly tells you about predictions of the object. So the static objects, you know that they will not move. However, for the dynamic objects, they are moving consistently with the time. And because we are also detecting lanes, you would like to know the lane's status. So is the lane beside you is free, so you can maneuver, or is not free, it's busy? Is the current lane free or busy? Do you have a lead vehicle to follow, and other lanes are closed or blocked for you? How about the traffic signs? How about the traffic lights? How close are you to your destination? Is there any upcoming exit? Is any upcoming entrance? And so on. And actually, there is a slide following for the system architecture, which I would give some more info about scene understanding in general. And then we have road segmentation, which tells you where are your road boundaries and what are your road widths. Then we have this depth estimation, either for objects or for how long is the road. And then we have the infrastructure detection. So in general, traffic lights, rules, traffic signs, road marks, the road curbs, the curbs of the road. And then we have lane detection for the current lane, not for other lanes. And we have a variant of, so in general, we have different variants for each team, but we have a variant for the S&B, which we can actually estimate virtual lanes for some times. So it is not only lane-based approach, but we can maintain virtual lanes for some times. And then we have the usual feature extraction from the photo using cameras, which is could be helpful for projection and for fusion in the localization, for example. For the first phase, we are targeting, or what I wrote here is that we are targeting, but that is what we actually achieved. So we can say targeting and achieved a coverage of 100 meters, so a circle of 100 meters with redundancy in front and rear. However, with a region inside with no redundancy, and I can say between 0.5 mean average precision. Okay. The platform we used TensorFlow or TensorRT for real-time application, CUDA deep learning, DNN, and some classical approaches. So we are not totally based on AI. We have some tasks that are based on classical and straightforward approaches. And for image processing, OpenCV for sure. Then we have the driving logic. So as I have said, a driving logic architecture is mainly based on localization and bus planning. So localization layer and perception and bus planning layer were developed and tested in Carla before deployment on a real environment. So during the development of the process, we had an AI team working on the perception, gathering some data sets, knowing how the sensor should work. And we had the driving logic team, which used the Carla as it is an open source environment. You could deploy cameras, you could deploy LiDARs, you could deploy IMU, you could even deploy GPS. So it is really fantastic environment to test your algorithms before deploying on a real environment or a real vehicle. And then we have the third variant, the motion control, which we're already working on the vehicle, getting the vehicle done for control. What we have today for localization, we have a fusion based on stereo cameras, GPS, two IMUs, one from the GPS, one from the vehicle, and wheel speed sensors. For the bus planning, we are really following a standard approach with some, we can say, some rules or some tolerance for either the driving laws or the driving behavior in general. And I know it is really hard to constrain the driver's behavior, but for the current demo, we have managed to do so. And so a hierarchical bus planning with some tolerance for virtual lanes estimation. So we can estimate virtually the lanes for some specific amount of time or some specific distance. However, after this distance, we just ask the driver to take back the control. Not because we are not able of estimating, but it is the safest thing to do so. And we have another variant as well that is not based on lanes approach. And as I have said earlier, we have a redundant driving logic, which is completely following another. So the inputs are the same, but the logic or the algorithm is different. We target for the first phase an accuracy of plus or minus meters for lateral and longitudinal distance, and I know it is hard to achieve. So if for the ones who are familiar with self-driving in general, it is hard to achieve that accuracy. And to be honest, we didn't achieve it in all situations. So mainly we are achieving this accuracy in a good lighting environment. And I can say a good example is if you have seen in the demo, the vehicle bypassed the gate, which is already didn't include any tolerance. So if there is the accuracy was more than 1 meter, would probably go into the gate or go into the road curb, which didn't actually happen in the video. And then we have the motion control, mainly about the development of longitudinal and lateral control. And this as well were tested and simulated in Carla before deployment on real environment. So they're actually simulated in Carla and further on tested on MATLAB. And then we have the application layer of the application development, which controls the mission initiation, pickup location, destination, and we have two variants based on if there is an existing map or not. So because in mainly I mentioned things that were questioned to me before, because there were some students asking if we are an IoT based or are mainly based on IoT or Internet of Things and so on. Currently, we are not based on Internet of Things, or we don't send any control commands to the vehicle. We just send the pickup location and the destination. However, we are not sending a route because we have two variants. One which is already based that we have an existing map, which can be open drive map, for example, and one which can be that we already mapped the environment before. So we mapped the environment before, so we have an existing map and we are following this map. So we have multiple variants, but we don't send any control commands to the vehicle, and we do not send any trajectory to the vehicle for the time being. So I'm just talking about for the time being. Later on, we can send a trajectory or where the vehicle should move. Based that you have like a high level map and you have a fleet of autonomous cars and you would like to manage this fleet. So it will not be only IoT, it will be Internet of Vehicles. This application for the current being, it provides some feedback to the user, how the system is doing, the detected objects, the vehicle speed, the steering inputs, and so on. The environment model in general with some useful feedback to the user. It can provide warnings as well. And we were working on a variant that can that can make the vehicle go to a complete stop in case of safety. And we were working on a variant as well to control the vehicle from outside the car. So if someone want to like remotely control his vehicle from the application. So let's talk about the system functions. So let's start with the perception. In the perception, as I have said, we are a solution based on cameras and radars. So we have cameras object detection, we have radars object detection. So we have one unified network that takes the inputs of all cameras and all radars. So we have a network for cameras object detection and one for radars object detection. And then we have features detection, which is only based on the cameras. And we have what we call surroundings awareness. So it's about infrastructure detection and road segmentation, segmenting the road between different objects. And then these inputs goes to the two main blocks, the instant object and detection tracking and sensor fusion. So the sensor fusion in general do two things. Increases the confidence level for each detected object, and then gives each detected object an ID, which makes it capable of tracking the object for further frames. And for example, it is we have put some constraints for this fusion, like there is no three objects on top of each other, or if this object is static, it cannot appear in different frames, and so on. We could estimate the other vehicle speeds as well from the frames and the detection. And then we have the camera calibration parameters, which is mainly a storage for the calibration parameters for the cameras. And then we have the function block, which is about the detection of lanes and the virtual lanes estimations. And then we have depth estimation using cameras, of course. And when we talk of depths right here, we are mentioning the depths of objects. And we have a technique as well to calculate the road widths or the lane widths in general. And then we have what we call the modulator or the logic of the perception, which is the scene understanding. Mainly, it gives you some hazards. So it gives you an awareness of the situation in general. So it tells you the objects, its tracking ID. It gives you a hazards level 1 to 4, for example. It gives you like the location of this object with respect to the vehicle global location, and so on. So anything related to the environment will come from the scene understanding, because we are using some hierarchical approach. Then comes the localization and mapping. So our solution today, we have a fusion between the classical odometry, which is involved with the integration between GPS, IMU, and wheel speed sensors, and later on we can add the steering wheel inputs as well. And we have the visual localization, which is based on cameras. In other words, we are using SLAM, simultaneous localization and mapping, so we don't have to have a predefined map before engaging your autonomous system, because we are simultaneously mapping and localizing ourselves on that map. And even so, if you already map the environment, it will enhance the localization architecture much more, because when we do the map, we do some certain optimizing techniques in map creation, which optimize the maps and verify the loop closure, and so on. So it is not an HD map, it is a SLAM map, which we can use later on when we engage the autonomous system to further enhance the accuracy of localization. And then we have a really classical approach for bus planning. We have a behavior planner, which is some rules and state machines, and we have local planner, which provides you a velocity profile and trajectory to follow. And we have the safety monitor, and we have the mission initiator, which tells you what pickup, what destination, and what lookup waypoints you would like to follow. And then we have the longitudinal and lateral control for longitudinal and lateral motion. And then we have the Flash application. So sorry, Flash is like the company name, but not the product name. So when we talk about the project in the company, we say Flash because Flash is one of my favorite heroes. So we have the application, and then we have the layer which is vehicle independent or vehicle dependent, which involves the throttle and brakes controller, the vehicle feedback, and the steering controller, and how to manipulate your vehicle in general to control several functions. Challenges faced. So actually, we faced a lot of challenges in addition to the usual non-technical challenges because, as I was saying in the start, for the demo or for the current phase, we couldn't test in an open environment. Not the reason is not that we cannot do so, but we don't have approvals to do so. We only have approvals to test in closed environment and the area around the closed environment. That's why, for example, you don't see much vehicles in the demo. However, we already have some videos and some data sets with a lot of vehicles and a lot of simulations involved. However, when it comes to actual testing, we were really constrained by the environment we have because of the approvals from the government and so on. So this is one of the non-technical challenges. Another thing is we are trying to do something which takes like 2 years of development at least. So when you want to achieve something really big, which takes a lot of time, and you have like a lot of competitors already starting the R&D process and starting developing self-driving cars from 2 and 3 years, it is really hard for you to adapt to this environment quickly. So you'll have to pressure on yourself and on your team to do extra hours and so on. So if you are not aligned on the same vision, you will not be capable of doing so. So I would like to say the challenges as follows. So overall challenges: S&B, DL, and motion control. So overall, which is really hard, is controlling a vehicle without ADAS features. So our solution currently is an aftermarket solution. So we have the sensor setup, we deploy in the vehicle, and we manipulate the vehicle or convince the vehicle that we are engaging the cruise control, for example, to give an acceleration or deceleration. But you don't have like a specific control for deceleration or acceleration rates, for example. And if the vehicle doesn't have any ADAS features enabled, or not, so if you buy a variant of the vehicle that doesn't have cruise control for example, so we not have a cruise control ECU. So how you can control an ECU that doesn't exist? That's one of the really complex challenges for us. Another thing is the door lock. So when the vehicle comes to you, what will unlock the doors? And when you start the vehicle, who will do the gear shifting from park to drive? Who will ignite the vehicle? So who will turn on the vehicle? Should be already turned on. And then how about the fuel consumption? A lot of consideration because our solution is aftermarket. You don't have and you don't do your own vehicle. That's why you are constrained by the platform itself. And then the installation of the sensors on the vehicle. So for those who saw the video, we installed the sensors on a metal sheet and some metallic bars, which we call, I don't know the exact name in English, but we don't have this network of metallic bars deployed in Audi vehicles. So the Audi vehicle doesn't have these metal bars. We had to manufacture them, and we had to install the metallic sheet with those metallic bars to install the sensors. Getting all the modules to run real time is really a tough problem, because you have to compromise between performance, between the timing, and the budget constraints. Because we had a budget constraint, and we had a timing constraint as well. So timing of development, and when it comes to integration between different modules, because when you test your module on Carla, for example, or if you test your module on a real environment, independently of the other module, the module works fine and you are really happy that it works. But when it comes to integration, there's a lot of delay, which makes the system behaves in abnormal behaviors. Handling corner cases. So in simulation or in general, because you are a first experience to the self-driving environment, you don't see the corner situation. So as a driver, you can see corner situations or uncommon situations every day. But when it comes to development, there's further corner situation because the cameras are not like your eyes, for example. No well-defined vehicle model because we are using already a vehicle. We don't know its non-linearities for each system, so we cannot actuate it in a proper way. Not in a proper way, but we don't have full access to control. For sensing and perception, data sets, because we have unusual classes in Egypt, so we have vehicles with 3 wheels, we have carrots, we have a lot of unusual classes on Egypt, so how to handle these classes. Strong sunlight, strong sun reflection, because for example, the asphalt color is different from one street to another. The road width is different from one road to another. How to optimize your heavily computational networks to run real time on your platform. How to project your sensors together, since we don't have like a good, not good, but as we are an aftermarket solution, we don't have like you are orienting your sensor as much as possible as real to the real environment. So we use the simulation environment, we put the vehicle inside the simulation environment, and we use the sensors. But you don't know the actual orientation as exact as real because you are deploying them aftermarket. So we attach the radars to the bumper, to the front and the rear bumper, and by common sense they are as much as like as real environment. But when it comes to projection, you need this projection matrix, for example, for sensor fusion. You need to be as exact as possible. Lane detection with respect to different kind of roads. So as I said, there is strong sunlight. There is the road width is changing. For the driving logic, we can say testing and verifying the localization accuracy in real life. So how you verify that the vehicle with respect to the global coordinates, a well-known global coordinates, follow your accuracy requirements. How you do so, and if so, how you optimize the fusion algorithm between different sensors. So we have like 5 different sensors and the data is not are not the same. So the cameras gives you images, GPS gives you longitudinal and lateral data, the wheel speed sensors gives you the rotational rate of the wheels, the IMU gives you acceleration and gyroscope rates. So how to optimize your fusion algorithm. How to pass some laws to constrain the bus planning or safety constraints. So we have a hierarchical bus planning, how to tell the bus planning that you should not exceed the traffic lights and the traffic speed. How you constrain it to not generate a collision-free bus. This is easy, relatively easy, but how to avoid generating a bus that can collide with upcoming vehicles, with upcoming dynamic vehicles. So in this frame, there's no issue with this bus. However, in 5 frames, there will be an issue because there's a dynamic vehicle coming with a specific speed which is higher than your speed. How to integrate waypoints if there's a map and if there's not a map. So when to go or when to switch between a map-based approach and non-map-based approach, and when to go with a lane-based approach and when not to go with lane-based approach. For the motion control, this is the last thing. Mainly if you let's say if you localize yourself not in a global coordinates but in a vehicle coordinates, so an XY on the vehicle, then the way you localize yourself would affect dramatically your choice of motion control algorithms. So, for example, if you calculate, if your approach was based on a standard or a straightforward motion control algorithm, and you are localizing yourself based on XY domain of the vehicle. So imagine that you have, this is my hand and this is a straight road. If you are moving straight, then you have a specific X and Y for based on relative to the starting point. So how about if this is straight line, you moved right, then left, then right, then left. It is impossible that you will have the same X and Y's because you are just accumulating your distance in X and Y's. In that case, the straightforward approach is dramatically affected by noise, or it is not accurate in general. So if you choose a straightforward approach while you are localizing yourself with a basic approach, you will really suffer a lot because the localization info will not be always the same. And if you are mapping the environment, the way you are mapping the environment, so you are driving, in a good way, so you will have some localization data. And then when you are trying to replicate the data or go under this trajectory, you will not go under this trajectory because it will be affected of your motion control accuracy. Another thing is the non-linearity relation used to convert the steering input to the wheels. We didn't design this system, so we don't know any relations between the steering wheel and your steering input. So in general, there's non-linearity between your steering wheel and the steering given to the wheels itself, because there's a lot of losses goes through the mechanical losses and the motors and so on, and gears and so on. So there's a lot of losses. And there's a non-linearity relation that you should know to model this system, to know which steering torque will give you a specific steering angle. And then the steering torque effect as well given by the system varies based on different speeds. So if you are running at 80 kilometers per hour, we are doing we are opening the margin for the steering torque less than we are moving on 10 kilometers per hour. So if you are moving at 8 kilometers per hour, you will need a stronger steering torque. However, if you are moving at 80 kilometers per hour, you will need less steering torque because any slight change in the steering wheel will affect the vehicle lateral position. And then we have the restrictions on timing because, as I have said, we are already manipulating a function of the vehicle. So, for example, this function communicates through the common communication control, which is CAN. It has a timing constraint, so you have to give an input or a steering or a brakes or so on input within a specific timing. So, for example, 10 milliseconds or 20 milliseconds. So you are forced to complete your algorithm, or you will need a new reading every 10 milliseconds. So this puts like a huge timing constraint on yourself. So that if you design the vehicle, you can say, I will control the steering each 50 milliseconds, for example. And one of the hard things, lots of tuning. So motion control will usually takes lots of tunings when it comes on deployment on a real existing vehicle. And when we have all the challenges, you will have the platform limitations. So how about deploying multiple networks on the same camera source or the same radar source? How about deployment of classical approach or classical algorithm and AI approach on the same camera source? How about computational constraints versus real-time performance versus budget? This is a lot of constraints you should know. Because in general, no one will buy like a $100,000 solution. So what I would like to show right now is samples of how we faced those challenges. So what I have in the top regarding this challenge is the sunlight, strong sunlight reflection. So as you have seen at the left image, there is you can barely see the lanes. Actually, no lanes. and on the right image, there is somehow lanes, at least the middle line is visible. And this is one of our implemented complex filters. So in general, for sunlights, we have a hardware and a software filter. This is an example for the software filter, one of the implemented software filters, which can be patent later, for example. And then we have an example which involves the vehicle. So this is what actually talk to manipulate the vehicle. So as you have seen here, there is a lot of wires, and this is one ECU of the vehicle. So it is really, I do not recommend anyone to do what you are seeing in the video right now, because it is really dangerous and it can risk your life. Because at the right here is the airbags, is the vehicle airbags, one of the airbags. So unless you are professional or know what you are actually trying to do, don't do this at all. And on the right, this is one of our team member. He is not a mechanics guy, so he's a system engineer. But this is an example of what it took to control the vehicle. So as you are seeing right here, there's an ECU and there's some jumpers. And what we are trying to do right here is to mimic the cruise control. So we are trying to mimic the cruise control at 50 km/h in a city road environment, so which I don't really recommend at all. Those are some insights across development. So this is regarding the simulation of localization based on the fusion, as I have said, on Carla environment. And what you are going to see here is a SLAM map or a SLAM environment. So I would just, because I think we have some time constraints, I will, yeah. So as you have seen here, there are feature points generated by the cameras. And we are trying to create like a LiDAR environment. So it is not a LiDAR environment, but something as similar as point cloud, but they are actually feature points or key points. And this is, let's see the lane detection algorithm. I'm just showing some insight which involves one of complex examples in general. So in our cross environment, we had an issue because there were a lot of 90 degrees curvature. So it was really hard to keep your lane or detect your lane on this curvature. That's why I'm showing this hard example to prove that we already have done a lot of work, but not all of them are shown on the demo. This is the vehicle in dark conditions or non-lighting conditions. I was just photographing the vehicle. So we have taken the curve smoothly, but we are not following the lane in this specific variant. And then we have here the first autonomous lab. So it was really in the first variant of our test track. It was in a sand track. So I'm just explaining what we are going to do. So I'm just turning on the vehicle and put the vehicle on the drives, and the vehicle switches lane, and then there is an upcoming U-turn. The vehicle will take it, and then we will stop after the U-turn. So this is usually back in March, I think, or February, not really sure. I am just showing that I am not, my hands are not on the steering wheel. So. And this, the top here is one of our first insights or in first variant. We are controlling the vehicle using Xbox controller, showing that we successfully can control the vehicle from any kind of signal, message, or whatever communication used. So we have a button for engagement of the autonomous system. We have a button to decelerate. We have a button to accelerate, and we have a button to steer left and right. So I will just escape to the video. I was just explaining a lot. That's why the video. Yeah. Okay, so I'm engaging the autonomous system right now, and I'm steering. And I'm not expert at driving the vehicle. That's why you will see that driver, which is one of our team, is always panicking, and he should panic. So he is trying to keep the steering wheel without any colliding. However, I'm trying to manipulate the vehicle as well. But anyway, he didn't touch the vehicle in this last second. I was me till the end controlling the vehicle. So what I would like to show here is our demo. I will just talk about the things that were not shown in the previous insights. So I think you have, or most of you have already seen it. We can escape this part. We have 6 cameras, as I have said, GPS antennas, 5 radars per each corner. Okay, so that's what I was saying, summon by app. We have an application which can be desktop or mobile variant. Give a pickup location and destination, and by the way, we have already our map, so it doesn't send the map. The vehicle enters the gate, and as you can see, if we, that's why I was claiming that our localization accuracy is within 1 meter, because if you can see here, it is really difficult to bypass this gate. You will either collide here or here. And in general, the shooting were done like 3 or 4 times. So these were actually tested, not that much, but tested as much as possible. So I just entered the vehicle here, and the vehicle should move to its destination. The destination in general is several locations in our test environment. So our test environment was in Silicon Waha, Burger Arab Smart Village in Alexandria. So our video is discussing about several features in the vehicle while we are trying to achieve level 4 autonomy. So the vehicle is just going through some known places in the environment and then going afterwards to the highway. So one thing that were not clear in the video, or we don't have specific videos right now, or we don't like to share a video for right now, is the object detection. So what you see here in the left is a fusion between the cameras and the radars. And if you have seen here, so this is the car detected by the camera and the radar, and if they are both detected, the color of the boundary box will be blue, and then you will see that the distance is 250. So we already 250 because we already detected it before this moment of the video. So this is not like compatible with each other. So. And here we are just doing an online maneuvering. And then we have like this 90-degree curve. Then we have a pedestrian crossing. So for this, we are not using segmentation to detect the pedestrian crossing. We have several tasks or several algorithms to detect the pedestrian crossing, but because we are just showing like different capabilities or different visualization, that's why we just put the boundary box on the segmented view. But we are not using in general segmented view segmentation detection of pedestrian crossing because it's not possible. And then we have the emergency braking. So the emergency braking in general as well is not only based on segmentation, object detection, and object detection in general with distance estimation. And why we use segmentation here? Because we would like only to brake on the persons are within the driving area. So if the person is outside the driving area, the vehicle can continue its driving. So we would like just to brake on on the interest of region of interest objects. Yeah, and back to the last. And here is just because we wanted to show the lane detection. By the way, this lane detection is done at two variants, 300 km/h and 80 km/h. And both I was at the passenger seat and I was just playing with my phone. I am not controlling the vehicle with my phone because you can imagine it is whatever accuracy you have, it is really risky and to control a vehicle on a highway with your phone. So that's why I showed you controlling the vehicle with an Xbox, how it would like to look like to control your vehicle through an Xbox. I mean, this vehicle variant. So I was just playing with my phone just to add some confidence that we are not manipulating the vehicle. I just open Facebook and so on. Okay, so what are our possible services? So mainly we have 4 categories. These are possible, but they are not like the fully agreed services with the management. But this is or customers, I mean. So we have four variants. We can sell our setup as an ADAS kits with different kind of sensors. It can include LiDAR as well based on customer needs. We can get different types of vehicles ready to be controlled via ADAS ECU. In general, drive-by-wire conversion might be applicable. And we have stacks, the usual stacks of ADAS. So separate features like the adaptive cruise control, emergency braking, lane keep assist, lane departure monitoring, blind spot monitoring, and so on. Or full stacks, which is our level between level 2 to 4. For perception, localization, bus planning, vehicle control, either according to ISO or QM, because as I have said before, we are mainly based on functional safety and system engineering. We have a third variant which involves simulation and mapping, HTML map creation, simulation content generation and setup, and data collection. And then we have an application-dependent variant. We can make remotely operated vehicles. We can make level 2 to 4 ODD variants. So we can make, like, for example, we can make a highway vehicle, level 4. We can make a racing vehicle. We can make a campus vehicle. We can make self-driving car fleets. And then our bigger vision is to have, like, first Egyptian autonomous electric buses or shuttles or so on. Sample of our deployed services right now. So it is already deployed to one of our customers in Dubai. So we are doing an HD mapping of highways and also generating a simulation content. So there is a supplier that sends us a raw data for 300 km/h, and we are developing OpenDrive maps and generates 3D FBX map that can be deployed in Carla. So what is the purpose of this in general? This could be one of the ways to validate your self-driving car algorithms before deploying them on a real environment. So this is one of the most hardest thing right now, or that the international community talks about. What verifies that your system will be safe enough? And that's why we are doing so. We are taking a real environment data, simulating it into Carla, and we are generating a custom algorithms or a custom scenarios. This is in general the idea of the project. So you can test your complex algorithm using on a real data with real estimations of the real data, and you can add your complex scenarios, and in that case, it could support you in your safety assessment. And this tool in general we call BrightTrack. Okay, so I think I have finished for today. We have like one slide to thank the team, and we have the Q&A section. So we can move to Ahmed.
We are all impressed about the great work and interesting delivery for the story, Mahmoud. Thanks for your time. We understand that the journey is long, and we are wishing you the best and your team to deliver the different variants you are planning for. Let's start with the questions from the questions are here. First question from Omar: is LiDAR allowed in Egypt?
Okay, so in general, all the sensors we imported are allowed by the Egyptian customers, and they were allowed because we are a research facility, and they were allowed because we will test them in a closed environment in a research lab. But when it comes to open environment, no, they are not allowed. And I think LiDAR follows the same idea.
Okay. Second question from Muhammad. He's asking about the vehicle radars. Are they the vehicle radars or use external ones? I think this was clear through the presentation, but you may
Yeah. Yes, so they are not provided on the vehicle, so they are external one, and they are aftermarket solution. That's why we already implemented them in front of the bumper, because if you put them inside the bumper, the radar waves will be reflected, and you will get actually no data, no data at all.
Okay. Another question from Ahmed Morsi. Do you use a special Egyptian environment model in Clara?
In Carla, okay, so in Carla, no, because in Carla gives you like 5 maps or 5 town maps. So for the current phase, no. However, with using BrightTrack, we can do so. So if we use BrightTrack, we can map the Egyptian environment and put it inside Carla, and we can generate complex scenarios as well.
Okay. We have many questions and interesting stories from Ahmed Dessouki. First thing, he said that you have mentioned that the team just bought the car. That means you don't have access to the vehicle model. How did you manage to tackle this using your motion planning and the control stages?
Okay. So in general,
I think first the question is separated from the second.
okay,
The question,
okay,
it is about
the
why
vehicle,
are
the
you
vehicle.
the vehicle
Okay.
itself?
Yeah. Okay. So let me answer this one first. So in general, we managed to tackle this problem using testing and validation. So we tested a lot of inputs. We tested the vehicle in different ranges of speed and with respect to different inputs to the steering wheel, and we noticed the reaction. And then we defined, we cannot say an identical vehicle model, but as much as possible to the vehicle model. Not everything in the vehicle model, to be honest, to just for example, to model how to model the steering torque to a specific steering angle in different speeds. So by testing and validation, we already had 2 months of testing, giving some certain cases, giving specific steering, noticing how the steering changes with the speed, and so on, while keeping some like tire inflation constant, for example. I mean, while trying to keep everything as constant as possible. So you don't just change a lot of things.
Okay. Next question as well. You mentioned that you are not sending trajectories to the vehicle at the current stage. If what is the significant influence of path planning on the pipeline?
Okay, so what I mentioned is we are not sending the vehicles through the application. However, it doesn't mean that we are not sending the trajectory. We are sending the trajectory. So we have a lot of ways. The first one is we map the environment, and then we map the environment previously, and then when we have the pickup and the location using geofencing, if the pickup location and the destination existed in the map environment, then you already generate a trajectory, which should be collision free. This is one approach. The second approach is to have like a map which is not an HD map. Sorry, I mean to have a map which is already an HD map, which we don't have today, for example. That's why I was saying that it is complex to have a mixture between a map approach and non-based map approach. So when you decide to follow a trajectory generated by your own environment model, by own mapping model, let's say mapping model, and then or to switch to an already mapped environment with good accuracy and so on, and when to switch, when to follow the lanes and when to not follow the lanes, just to follow a trajectory, for example, trajectory execution, not a lanes, non-lanes action.
Okay. Another point highlighting about E is only on parking maneuver. Is referring to some accident that happened by Uber autonomous car that was one while the autopilot was on. The automatic braking wasn't turned on, and after some investigation, they figured out that if the parking system was turned on, maybe this accident was avoided. Have you studied
Okay,
this?
okay, so okay. Okay, so electric parking braking is different from automatic emergency braking. So electric parking brakes, I have to say it by Arabic, so sorry for my my Arabic language, from اليد. So electric parking brakes, we only use electric parking brakes in situations that you have a low speed, like you are moving 8 kilometers per hour, and you have a time to collision less than 2 seconds. That's why in that case we allow the electric parking brakes to activate, because as I have said, they only activate on the rear vehicles. They only activate for the rear vehicles. However, for automatic emergency braking, we are opening. They are, let's say, we are opening the margin for automatic emergency braking for deceleration rate. For example, for our current vehicle, we can achieve about 7 meters per second deceleration rate. So in general, when you go to like 50 kilometers per hour to 30 kilometers per hour, you don't use the full deceleration rates. However, when you are going to complete stop, we open the throttle, or we open the margin for the full deceleration rate. Once you are under this range of 8 kilometers per hour, or the time to collision less than 2 seconds, you can allow the ABB or electric parking brakes to activate. So I'm not turning off the automatic emergency braking. However, we are not turning off the automatic emergency brake. However, we are manipulating the electric parking brakes. And by the way, the automatic emergency brakes doesn't have to always to use electric parking brakes, because it is really dangerous because in general it will it can make the vehicle turn over, because you will have like a torque on the rear wheels, and which is in a different direction than the torque on the front wheels. And in general, I'm not saying that it is completely safe 100%, but as I have said, you are already constrained by the vehicle. You cannot ask the vehicle to decelerate more, for example.
Okay, it's clear. Next question from Ahmed Morsi. Do you evaluate your KPIs within the simulation only, or do you use reference sensors?
Okay, I think there was a question before this, but it disappeared.
We will come to this question soon.
Okay. Do you use reference? Okay. So for the current being, we evaluated by simulation, and as much as possible data sets from real environment, as much as possible from our closed environment. But I cannot say that it is totally that I'm satisfied by the evaluation. But this is what we can do for the time being.
A second question from Ahmad also, do you collect data sets for your AI model? How do you collect data sets for your AI models?
So in general, we have we use open source data sets. Then we collect the data sets using the cameras and the radars and the GPS. So you have camera frames, radar cluster points with respect to the vehicle location.
Okay. Another question from Muhammad Hassan. Which onboard computer are you planning to use, NVIDIA or something else?
Can you repeat your question?
Which onboard computer are you using or
Okay.
planning to use, NVIDIA or something else?
I cannot answer this question because it
Okay.
is like confidential.
Okay, understand that. Okay. Okay, we have some questions also we received from the early beginning of the session. We can go
Okay.
for them.
Okay.
About open positions in Bright Skies and how to join your team from web.
Okay. So in general, for the first phase, we don't have open positions because already finished. For the second phase, it is expected that we may have open positions, but actually the second phase is delayed because of getting the required approvals from the environment. But to say in general, we may have, you can stay tuned at our LinkedIn web page and Facebook page to stay tuned for the open positions. It have to be in self-driving only. However, as you know, as we all know, because of the coronavirus situation, there are already many OEMs that closed, and this affected the whole automotive market. However, it is going to, I think, the corona situation is getting more better. So I think in the next year we would have an open positions.
Okay.
But I cannot predict when, to be honest.
Okay. Question from Salma. She is asking about getting some support or advice on how to import and buy radar sensors. If your company may help support on something like that, as she want to make a prototype of self-driving car in her graduation project.
Okay, so in general, for this year, we are not supporting any graduation officially till now because of the corona situation. We don't have enough employees. However, I will leave my contact at the last of the session, my LinkedIn contact for anyone who wants to know anything related to self-driving or anyone asks to help. I will be glad to help him or her.
Okay. Next question from Ahmad Hassan. What are courses which enable him to work as self-driving car engineer in practice?
Okay, so in general, every phase requires different qualifications. But if you are talking as a junior, I think self-driving car nano degree by Udacity would be a great choice. Comes after the self-driving car specialization by Coursera. Deep learning nano degree as well is a good choice.
Okay. I think we got some questions. While we are answering the questions, we can go over them. Hani is asking how easy difficult do you think porting your solutions to a different platform would be?
Okay, so what do you mean by different platform? Do you mean a different vehicle or a different controller? So I can go with both. So for if we are talking about the vehicle in general, if you are talking about the vehicle, we have as I have said in the presentation, we have two things. One which is vehicle dependent and one which is environment dependent. So this one for environment dependent, I think it would be the same for all vehicles. And what you have to change is just the vehicle dependent one. The difficulty depends how if the OEM is going to help you or not. If you have like an intuition of how to control the vehicle or not, or if you are doing this for the first time or not. if it is a variant that you have worked on before or not. One thing that helps us a lot to manipulate and control the vehicle, that we had a lot of engineers working in or periphery, I mean, working in other embedded companies, and also works in our company, which they had much experience related to automotive applications. So they know what to do, how the architecture look like, how the databases look like, how the function should interact, and so on. If you ask me about the platform which is controller dependent, right now we are using a control board which is based on OS, or OS you can consider like an Ubuntu. So if you have any Ubuntu environment, then you will have the classical difficulties, like getting the platform ready, the compatibilities, because you may have some libraries that work on some architecture on Ubuntu, but it doesn't work on others because of the different hardware architecture.
Okay. Next question from Dana. More about the role of mechanical engineers in Brightskies.
Okay, so if you are asking about the mechanical rules that we already published at our website, they were mainly not for this project. So for this project, we had an open position, but it was an internal position. Just we need a mechanical design engineer to design the sensors allocation and how to put them and how to manufacture the metallic bars and the material and so on, and what configuration should we put them to achieve the 360 coverage. So this is for my part. In general, for the mechanical engineers, we had like 3, I think, positions: 1 for technical manager and 2 for as engineers. We are working on a battery management system. So we needed such engineers to work on the cooling and to work on the design of the vehicle chassis and the design of the battery management system and so on.
Okay. Next question from Muhammad Hassan. Are you using open source algorithm for SLAM like SVO, or are you developing your own?
We tried both.
Okay, clear statement. Question from Edo. What computer used in the car and how to communicate with the original car's ECU?
How do you communicate and how do you design? Okay, so we didn't design drive-by-wire system for the current vehicle. We used the current ones in the vehicle, and we are communicating with them using CAN. It is not a confidential information because most of the vehicle in that period are communicating through CAN.
Okay, I think we covered the questions. Thanks a lot for your time and this interesting webinar. On behalf of the community, I'd like to thank Mahmoud for these entertaining presentations. We really appreciate you taking the time to be with us today. And thanks everyone. Hope to see you soon. And have a nice night.
Thank you. I just need to thank the whole team at the last, because behind every great achievement there is a great team. I am just a representative of the 14 engineers or more worked on that project, so I would like to thank them. And at the end, the contacts for me and for Brightskies are found on LinkedIn, as seen here. So thanks, Ahmed, as well for having me today.
You are welcome. And we encourage if they have much more questions, they can contact you directly on LinkedIn, and it will be a good opportunity to network with you and get much more information from you.
Yeah, for sure. I will be glad to do so.
Okay. Thanks a lot, all, and goodbye.
Thank you. Goodbye.